Right, okay. So let's welcome back to this module on wireless. So today we're going to continue our journey and look at the basics of wireless comms. Right, we're actually going to finish that part today, and then start moving to hopefully something you will find more interesting, which is really some MIMO processing. Just an announcement, so you're going to have, so today is our third lecture. Next week, you're going to have lecture number 4. That will be, as usual, on Thursday morning, 9 to 11. But you will have also the first class on Monday. So Monday, 25th, you're going to have the first class. And that's going to be with the GTAs Yang and Longfei. And it's going to be on the same channel. Right, so exactly the same teams. Right, so there you will go over some of those problem sheets. You will see, you will start playing with MATLAB as well. See how you can implement some of those techniques in MATLAB, and that's it. So make use of those sessions. Is very useful to get used to some more practical aspects of wireless, and then prepare for the coursework. Right. Any questions on so far what we have done? Right. So as usual, feel free to interrupt me. Right. Raise your hand, or directly interrupt me. Let's try to have something more interactive. So today let's continue with our MISO systems. So remember on Monday we talked about diversity, and we looked at SIMO when we had multiple receive antennas. We looked at different combining techniques, and then we finished the lecture on Monday with MISO systems, where we said, what if we have multiple antennas at the transmitter? What can we do in terms of design in order to capture some form of diversity? Right, and we looked at two cases, or I just introduced two cases: the case where we have perfect knowledge of the channels of the transmitter, and the case where we have no knowledge of the channels of the transmitter. Right? And what we did on Monday is just to look at the case where we have knowledge of the channels of the transmitter, and what we said is you have a system model that looks as follows. You have single receive antennas here, so you have a single observation. You have a vector channel, and now you have a transmitted signal that is a vector as well, and we write it simply as a pre-coded version of our transmitted signal, transmit symbol. Right? So C can be a transmit symbol, and then we pre-code it using W, and what we said is actually one way to design it to maximize the SNR is called maximum ratio transmission, which is reminiscent of what we did for the maximum ratio combining when we had the SIMO case, right? So essentially, similar to the MRC, we actually have a precoder now that is a function of age, but we actually take the Hermitian of this such that the transmit precoder essentially match the wireless channels, the channel vector. And this was due to the normalization, the transmit power constraint, in order to keep the transmit power capped to a constant. Right, so what we said is that if you do that and you plug this into this, what you end up with is a system model that looks like this. You have H multiplied by H Hermitian divided by the norm of H multiplied by C plus some noise. And so this here is equal to H, the norm square divided by the norm of H. So this is actually the norm of H. So you're going to have a SNR that will actually be proportional to the square of that norm, which is exactly what we had with the MRC. So you have something that looks like your SNR, instantaneous SNR is rho H squared, right? Right. So if you take the expectation of this is actually will be equal to your long-term SNR here, multiplied by the expectation of that term, which will be equal to nt, the number of transmit antennas, since each element of that vector is assumed to have a variance equal to 1, as we have done before, right? So you see all the tools we have looked at for the MRC, you can apply this to this case as well. So this actually, you're going to have essentially something that looks like some chi-square distributed random variable, and so you can compute the error probability of this kind of transmit diversity technique, and you end up with this, which is actually really the same as what we had with MRC. Right, if you go back to here, right, we had this kind of expression here, right, or this kind of expression here, that we were using the fact that our random variable u, which was again the here our norm of h, right, norm square, is actually chi-square distributed, and so you end up with actually similar expression. Instead of having an r as the number of receive antenna, now you have nt, the number of transmit antenna. Right, so you can directly use what we have done there before. Right, so now one important aspect of this you have to keep in mind is that to design your W, you need to know h at the transmitter. Right, so this is what you call channel state information at the transmitter. So your h is the channel state information, and you know this at the transmitter. So in practice, this is more complicated than MRC for the simple reason that if you have a transmitter and you have a receiver, and so you want to actually you have multiple transmit antennas here, you have this vector h there. And what you do in practice is there are two ways. One way is actually you estimate h at the receiver first using pilot. So you do channel estimation to the receiver, and then you actually quantize this h and you report this back at the transmitter, right? So this is what is done in 4G and 5G, and especially if you have FDD, so you have frequency division duplexing. That means actually your uplink and your downlink transmission are done on two different frequencies. This is the way you do it. You estimate h at the receiver, you quantize it, and then you report this quantized version back to the transmitter. So in practice, you never have h that is perfectly known at the transmitter. So this is one way. Another way is TDD. And in TDD, what you do, you actually the channels on the uplink and the downlink. So from the transmitter to the receiver, and on the uplink from the receiver to the transmitter, is the same because they operate on the same frequency band, but could be a different time instant. But actually, the channel is relatively stable. Then the uplink and the downlink channels are the same. So what is done there is to actually transmit pilots from the user. So I could call it this user terminal, and this is a base station. You transmit pilot from the user terminal to the base station. You estimate the channels on the uplink, and you say that your channels on the downlink is the same on the uplink because of reciprocity in TDD, and you use this to design your precoder for the downlink. Right. So this is what is done in practice. So you will see, you will play with this and quantize feedback in coursework 3. Right. So So one way to interpret this, when you do W multiplied by C, what do? You actually have, let's say, two transmit antennas, right? And you transmit a symbol C, but you pre-code it, right? So your W, let's say, is W1, W2 here with two transmit antennas. So what that means is actually you multiply C by here W1, and it goes to the first antenna. You multiply C by W2, and it goes to the second antenna. So physically speaking, what this does is essentially some form of beamforming. You actually beamform your symbol in a certain directions that is given by those weights W1 and W2, and those weights change as a function of the channel. Right? So if you have two antennas and you put some weight on those two antennas, you have seen in your undergraduate course, actually this creates a radiation pattern. And this pattern, for instance, could have a main lobe in a certain directions and then maybe some side lobe in some other directions. And by changing W1 and W2, essentially you change the directions of these lobes, right? And you do this in order to maximize the SNR at the receiver, right? So these W1 and W2, those lobes are not necessarily in the directions of the terminal, right? You can have a terminal here, but this lobe, this main lobe, is not necessarily directly in the direction of the terminal, because it depends really on those channel strength. So because H1 and H2, the element of H are random variable, it means actually even if you have someone in front of you, but you don't have, for instance, a direct line of sight, what you may prefer to do is, for instance, to beam something around that direction, is reflected around the wall, and then it goes towards the user, right? So your beam is not always directly pointing towards the receiver. It really depends on the propagation conditions. Okay, so so this is what happens physically speaking. Good. So so the other techniques, which is also a form of transmit diversity, but is now relying on not knowing the channels of the transmitter. So the question is, if you have a transmitter and a receiver, you have H. H will be known at the receiver to do coherent detections. That's always the case. But you don't want H to be known at the transmitter, because actually this can be a bit more complicated to implement. Or in some scenarios, if you have mobility, it becomes very complicated to obtain H, accurately at the transmitter. So you have other techniques that enables you to obtain some diversity gain without knowing H in the transmitter. And so the simplest case, the simplest scheme, is called the Alamouti scheme. It was invented by Alamouti in 1998, so now it's over 20 years old. And it's a very simple idea, but very powerful, and is nowadays used in all systems. Right, so I have to say this one is used as well, right? This technique is used as well in modern systems. I think probably, but so those two are used in probably starting from definitely 4G, maybe some aspect of it, maybe in 3G, but definitely in 4G and 5G. Now, how does that work? So this is something that you may have seen before. Maybe this was covered in advanced communication theory. So the idea is the following. So imagine you have your channel vector H that is made of two coefficients. So you have two transmit antennas and one receive antennas. And you want to make use of two successive symbol periods. So here, in this case here, you actually at every symbol period you can transmit a different symbol, right? What we do here is actually we assume that we have two successive symbol periods, and what we do is transmit two symbols across those two symbol periods, but we're going to transmit them twice in a way. So if I draw this a little bit, it's like you have, let me take this here, you have two transmit antennas, you have one receive antenna, right? And you're going to have a time t1 and a time t2, right? And what you're going to do is to transmit some symbol at time 1 on the first antenna, and the same symbol, slightly changed, will be transmitted at time 2 on the other antenna. And then you're going to have another symbol that will be transmitted at time 1 on the second antenna, and a slightly different version of this will be transmitted at time 2 on the first antenna. So you will still transmit one symbol per symbol duration, if you like, per symbol period. But instead of transmitting one per symbol period, you're actually going to transmit two per two symbol periods, right? In using form of matrix. So let's see how this works. So what we do is the first time instance, we transmit two symbols C1 and C2. So what I'm doing here, essentially, instead of having those shapes, I'm going to transmit C1 and I'm going to transmit C2. So let me erase those for the time being. Right? So I transmit C1 from antenna 1 and C2 on antenna 2. And then on the second time instance, I will transmit here minus C2 conjugate and C1 conjugate. Right? So same symbol, but we are now conjugate them, and I put a minus there, and I will show you later on why we do that. Right? You will understand in a minute. Right? So what is the idea here? Intuitively, is that let's imagine I have a fading channels here, so I have a coefficient H1 and H2. C1 is transmitted from the first antenna, and then it's transmitted from the second antenna. The idea there is to make sure that C1 travels through both paths, both antennas, so that if one of them is weak, let's say H1 is very weak, right? C1 will be very badly received at the receiver because it will travel through H1. But at the next time instance, C1 will transmit through H2, which is likely to be better, right, than H1. So imagine you have a case where, for instance, you have H1 is like this, but H2 is like this, right? And you have this time instance here, right? So you have something that is good for antenna 2, bad for antenna 1. And so you want to make sure that actually C1 travels through both paths in order to have at least one of those two will be good enough, right? And the same for C2, you see it travels through H1 and H2. Now we're going to assume that H1 and H2 here are constant over those two time instants, right? So I'm going to have the time T1 here, for instance, and I'm going to have the time T2 there, right? So it's constant. So the channel antenna 2 here, H2 is good for both time instants, and H1 will be bad for both time instants, for instance. So we'll see later on why this is important for H1 and H2 to be constant over those two symbol duration. So if we do this, let's look at our received signal, right? We have two symbol periods, so we're going to have two observations at time T1 and at time T2. So I'm going to have C1 multiplied by H1 plus C2 multiplied by H2. That's what is received at the receiver. That's what I see here. C1 multiplied by H1, C2 multiplied by H2 plus some noise. Okay. Now I have my usual square root of ES, but I have here a square root of 2, right? And the reason for this is because, again, I want to normalize my transmit power. So C1 and C2 are chosen, for instance, from a unit average energy constellation. But if I don't use the square root of 2, it means that I would transmit twice as much power as if I was transmitting only across one antenna, right? So I'm just normalizing with the square root of 2 in order to keep the number, the transmit power constant, irrespectively of the number of transmit antennas. Right, so so what happens in the second symbol period, time 2, now I transmit C1 conjugate from antenna 2. So I'm going to have C1 conjugate will be multiplied by H2, and minus C2 conjugate will be multiplied by H1. Right, and I have my second observation with a different noise realization. Those two nodes are independent of two time instances. Right. Now I can write this in a matrix form. And before doing this, what I do first is I write this slightly differently in the following form. I'm say I will conjugate Y2. So if I conjugate Y2, and I will change the order here, right? So I'm going to have ES H2 conjugate C1 divided by square root of 2 plus, not plus, minus ES H1 conjugate C2 divided by square root of 2 plus the conjugate of the noise, right? And now what I see is that actually I have two observations and I have two transmitted symbols. I have C1 and C2, and here I had C1 and C2. So I can write this in a matrix form. You have two inputs and two outputs. So I have my two outputs are Y1 and Y2 conjugate. My two inputs are this one, C1 and C2, and here C1 and C2. Right, so I can write this in a vector. And now I can write my effective channel matrix here. I'm going to have at the first time instance C1 and C2 will be multiplied by H1 and H2. That's why I have H1 and H2. Second time instant, after the conjugation, I have my channels. C1 is multiplied by H2 conjugate, so I have H2 conjugate, and C2 is multiplied by minus H1 conjugate, Right. Good. Now I have an effective 2-by-2 system. 2 inputs, 2 outputs. Now, what's the nice things with this? And what is the reason why we have this conjugate and this minus and so on? Is because of the following. If you take this matrix here, take one more page. Right, if I take this matrix H effective, so let me write this. H effective is H1, H2, H2 conjugate minus H1 conjugate. And let me write now H effective, the conjugate of this, the Hermitian of this, so transpose conjugate. I'm going to have H1 conjugate, the transpose N conjugate, H2 conjugate, H2, and minus H1. Right. And what happens if I do H effective Hermitian multiplied by H effective? So what do we have? We take here this row multiplied by this column, right? So I'm going to have H1 squared, this one multiplied by this, plus this one multiplied by this. That's going to give me this. Right? I'm going to have a 2-by-2 matrix. If I do this row multiplied by this column, so this row multiplied by this column, I have H1 conjugate multiplied by H2 plus H2 multiplied by minus H1 conjugate, minus H1 conjugate H2. If I do this one multiplied by this, I have one here, this one multiplied by this, what do I have here? I have H2 conjugate H1 minus H1 H2 conjugate. And if I deduce this multiplied by that, I have H2 squared plus H1 squared. Right? So what you see here is this is equal to 0, this is equal to 0. Okay, so this is nice because now I have this expression is essentially H1 squared plus H2 squared multiplied by an identity matrix size 2. And this is the norm of H, the norm square of H. Okay, so what happens is that at the receiver, now you can simply multiply by this. So you multiply by this quantity, your Y here, you multiply by this. And what you end up with is just a matrix now that is diagonal, a scale diagonal matrix here, effectively. And you have C1 and C2. So that means actually C1 and C2 can be decoded from those two observations, and they will not interfere with each other, right? In this case here, your Y, your observation, you see that actually if you want to decode C1 from W1, well, you have actually interference from C2, right? So you're going to have to do joint decoding of C1 and C2 if you want to actually, you just rely on this. But if you do simple linear processing here at the receiver, what's happening is that you have Z1 here will be simply equal to ES multiplied by the norm of H, C1, the square root of 2, plus some effective noise, I call it NY prime. And then I have Z2 is this multiplied by the norm of H, C2 square root of 2 plus N2, right? C1 and C2 are completely decoupled from each other. So I can decode C1 from the first effective observation here, Z1, and I can decode C2 from this. How can I do this? By simply doing a maximum likelihood detection exactly in the same way as what we did earlier on, the SISO case. So the same as if you have single transmit antenna and single receive antenna, just in the same way as what we did in last lecture using that. Okay, so you can apply this, you can do this for each of those receivers. It will not be exactly H here. We're going to have H, the norm of H, but it's the same idea. So you can write a detection here, something like this. Oops. Right, what you can write is you're going to have essentially Z1 minus expectation of SH square C1 over square root of 2, right? And you maximize or you minimize this. So you find C1 that minimizes that quantity, right? Simply, you can do the same for C2, right? So those two are decoupled, right? Now, what you see from this is that you have effectively a channel matrix after this processing that is equal to this norm, that is equal to this here, right? So what is the diversity order, diversity gain that we expect from this? Right, if you think about what we did before, any idea, anyone? No one? So you're going to have a diversity gain of 2, right? Because, again, this looks like exactly what we had before with maximum ratio transmission or maximum ratio combining, right? This would give us a diversity gain of 2, right? So here you're able to have a diversity gain of 2, despite the fact that you don't have any channel knowledge to the transmitter. That's the same as what we had here. Here we had a diversity gain of NT. So if you have 2 transmit antennas, you have a diversity gain of 2 when you do the match beamforming of maximum ratio transmission. But there you need to know the channel of the transmitter. Here you don't know the channel of the transmitter, but you will still get a diversity gain of 2, right? So you can compute the SINR, right? It's going to be the SINR here. I'm going to have the SINR here of, after this processing, I have ESH square divided by the square root of the noise. So actually you're going to have a square here. If you compute this, you're going to have also something that will be functional to H1 and H2. When you take this and you divide by this, actually you're going to end up with this. You can do this at home. There is no major complexity here. So you're going to end up with instantaneous SNR that is actually given by this, and you have additionally a 2 there that comes from the square root of 2, right? So you end up with rho multiplied by h squared divided by 2, right? This is what actually we have here. Now, if you take the expectation of this, so this is our output SNR, right? The output, the SNR at Z1 and Z2, Z2 will experience the same thing. If you take the expectation of this, so if you take the expectation of the output SNR, what we're going to have is rho divided by 2 expectation of this, and I have 2 transmit antennas, so this will be equal to 2, so that's going to be equal to rho. Right, so what's happening here is that you see you don't have any array gain. Your output SNR after processing is the same as your single branch SNR. This is different from what we had here with the transmit beamforming or the transmit MRC. We had an output SNR. The average output SNR is actually NT times the single branch SNR. Right? So this gap here, this one here, if you have 2 transmit antenna, the output SNR will be actually twice as large as what you get with Alamouti. And the reason is because here you have knowledge of the channel of the transmitter. Here you don't have the knowledge of the channel of the transmitter. So what that means is that those 2 schemes, the transmit beamforming, transmit maximum ratio transmission, and the Alamouti, will have the same slope in terms of error rate versus SNR. They have the same slope, but there will be a gap of 3 dB between them because the output SNR of the transmit beamforming is actually 3 dB higher than the one of the Alamouti schemes. Right? And the reason is because you don't have channel knowledge of the transmitter. And so here in this case, you can actually form a beamformer. You can beam your energy in a certain directions. In this case, you cannot do that because you don't have knowledge of the channel transmitter. Right? So that's the main difference. Right? So because of this here, because of this kind of expression, you can write your error probability also very easily. This is going to be chi-square distributed, right? Again, as we have done before. So you can use the moment generating function that we have done before with MRC and compute your error probability. And it's going to be the same as with MRC. The difference is that instead of having a 4, you're going to have an 8 there. So you remember with MRC, again, what we did last Monday, we had here a 4, right? Your minimum distance divided by 4 to the power minus nr. Now, instead of having 4, I'm going to have 8 because I divided C1 and C2 by square root of 2 to maintain the transmit power constraint. And I'm going to have, instead of having nr, I'm going to have now 2 because I have 2 transmit antennas. So this is what you see here. This is your error probability of Alamouti schemes for an upper bound of the error probability, symbol error probability when you have 2 transmit antennas, right? So this is what you have here. This is a symbol error rate versus SNR. This is done with BPSK over relay fading channels, so IID relay fading. So that means actually the coefficients again are circularly symmetric complex Gaussian random variable. They're independent among the antennas. And what you see here is that you have so that's a SISO case with fading, with relay fading. There is no spatial diversity gain. So that means that actually at high SNR here, the decay here will be at 1 over rho. This is your SNR, this is our rho. So that means actually if I increase by 10 dB, by 10 rho, my error rate will decrease by 10. And you can see it roughly if I draw a straight line here, something like this. Right? You can imagine you go from 10 to the minus 1 here to roughly 10 to the minus 2. And you will go from 4 dB SNR to roughly 14 dB SNR, right? So if you increase by 10 dB or increase the SNR by 10, essentially your error probability will fall only by a factor of 10, right? If you go to those two, now we have 2 transmit antennas. This line here, this is with Alamouti scheme. This line here is the transmit beamforming or maximum ratio transmission. So here you see that the slope has been increased. And again, if you draw a straight line here, right, and you will do this in the coursework, but you're going to have to go over a wider SNR range in order to really measure this properly. But you will be able to see that if you increase by 10 dB, right, so you're going to go from something that goes from something minus, I don't know, 3 10 to the minus 2 to something that probably will be 3 10 to the minus 4. So you will have your increase your SNR by 10 dB, your error rate will fall by a factor of 100, right? That means actually this slope is in 1 over rho square. Right? Similarly here, you see those two curves are parallel with each other, so they have the same slope, also 1 over rho square, but you have 3 dB gap. You see here from this point to this point here, right? You're going to have a 3 dB gap that corresponds from 10 dB to 7 dB. You have 3 dB gap that comes from the fact that here your average output SNR is just equal to your single branch SNR, but in the maximum ratio transmission, we had our average output SNR is actually 2 times rho. So you have in the log domain, you're going to have actually 3 dB gain. Okay, so this is very useful, very practical schemes. Right, so where do you use this? So typically, if you know the channel of the transmitter and you have probably relatively low mobility, you would use transmit beamforming. If you don't have your channels of the transmitter, you would use Alamouti schemes. So high mobility, probably you will use Alamouti schemes, as long as your channels are constant over the two symbol duration. You can use this also in real system. You can use over what is called control channels. So control channels are actually the backbone of the systems that need to transmit information from a transmitter to a receiver that are not data per se, like it's not like your YouTube video, but actually information that are critical for the receiver to know in order to decode your data properly. right? It's this what is called control information. The way those control data are transmitted is using very reliable transmission schemes, and one of them is these Alamouti schemes. Right, so one thing I have to mention is the following. I mentioned here that our channels is constant, right, over 2 successive time instants. What happens if it's not the case? Well, what happens is the following. If H1 change a little bit, you see, instead of having you have H1 here, at the second time instant, you will not have H1. You will have H1 plus, H1 will become H1 plus epsilon, for instance. And here, second time instant, you may have H2 will become H2 plus epsilon, right? So that means actually when you compute this here, instead of having H2 here and H1 there, you're going to have H2 plus epsilon, H1 plus epsilon. And what happens is that when you do this, right, when you do this operation, if your channel is changed a little bit on the second time instant, those terms here will not be equal to zeros anymore. They will be slightly different than 0. And if the gap between the channels on the 2 time instant is increasing, then the values of those 2 coefficients here becomes much larger than much different than 0. And so in other words, what that means is that now you cannot simply use Z1 to decode C1, because you're going to have interference from the other streams from C2. Right. And in that case, what you need to do is you need to do joint detections of those 2 streams, and this is what we're going to do later on when we do MIMO. But that increases the processing, because instead of having 2 maximum likelihood decoder here for each of C1 and C2, now you need to go over, do a joint maximum likelihood detection over both streams C1 and C2. And that will increase the complexity of the receiver. Right. Good. So one more thing here, indirect transmit diversity. So there are other techniques. I will not go into those details, but if you're interested, you can see in the book. So what we talked about here is really spatial domain, but you can use 2 transmit antennas to convert your spatial domain diversity into another diversity, another domain. And so one of them is called delay diversity. And by doing a specific scheme, you will see actually it's listed in the problem sheet. You will convert spatial diversity into frequency diversity. So if your channels change in the frequency domain between frequency 1 and frequency 2, you can leverage this behavior to exploit the diversity gain as well, now in the frequency domain, right? You can have other schemes that are called phase rotated, so where you convert those spatial domain diversity into a time diversity. So effectively, you convert frequency spatial domain into channels that change over time, and because it changes over time in a certain way, you can actually exploit time diversity. Right? So there are different schemes that exist. They have different benefit. Everything is explained in the book. If you're interested in those ones, it's also used in practice quite extensively. Another way, if you have time diversity, if your channels change over time, what you can do is that you can use what is called interleaving and error correcting codes in order to exploit this diversity in the time domain. So this also can be done. So this is explained in the book, especially in the MIMO book. But I will not go into this. Unfortunately, we don't have time in these modules to go into all those different techniques. Right. So that's it for let's say MISO and SIMO, the time being. And now what I'm going to do, I'm going to start looking at the last part of the last section of this part 1, which is the capacity of wireless channels. So what is the maximum amount of information that we can reliably transmit over a wireless channel? And we're going to reuse the system model that we had before. So we're going to reuse this. And I'm going to look at here, assume that I'm going to have only the small scale fading. Again, you can always add the large scale fading, the path loss and shadowing, but it does not fundamentally change the mathematics behind. Right, so I'm going to have, I received observation. I'm going to have, for the time being, for most of it, I will assume SISO transmission. So I'm going to have single observation here and a single transmit antennas and a single symbol that actually is transmitted. I have a receive observation at time k. I'm going to have a chance coefficient could be time k. I have my AWG noise, and I'm going to have, as usual, our average SNR is ES divided by the variance of the noise. And I will assume that I have, as usual, our power constraint. So this means here that our CK comes from a unit average energy, unit average energy constellation. And we're going to look at 3 different scenarios. The first one is when we have a deterministic channel. So that means that my channel H actually does not change over time. So I can drop the K there, and it's just constant over time, right? And the capacity in that case is quite straightforward. It's really the Shannon expression that you have seen already before. And then we're going to look at 2 other scenarios and see what happens. The case where we have slow fading and the case where we have fast fading. So what does that mean? It means the following. I'm going to have a channels that potentially can change over time. So this is my time K. And I'm going to have a channels, for instance, that will be there, then will be there, then will be there, will be there, will be there. So this may be a time, say time 1, time 2, time 3, time 4, time 5. It changes over time, right? And it has a certain length. I assume actually I have a kind of block fading channel. So actually it means actually I change. It's constant over a block, and then it changes from block to block, something like this, right? Just approximate, just to illustrate what's happening. And so the slow fading case, it means actually when my channel is constant here over a certain block, it means that I can slow fading will mean actually I can my encoder, the output of my encoder, so my block code will actually be transmitted over a single realization of these channels. So I will transmit actually encoded packet that will be actually transmitted over a single realization. So the length of that packet maybe, for instance, is very small here compared to the length of the occurrence time of that channels, right? So let's imagine the length occurrence time of the channels here is this. This is what I have here. So the channel is constant over this period of time, over this block. And the slow fading, I will just assume that any form of coding, the duration of that block, code block will actually be small compared to the occurrence time. In the fast fading, it means that potentially I could encode information over multiple realization of the channels. And so in that case, my block code could, for instance, span this duration, and it will actually be encoded. The encoded packet will actually be transmitted over multiple realization of the channel. And so we'll see that this leads to 2 different architectures and 2 different ways of actually measuring the performance as well. Right, so let's start with the simplest case here first. I have a deterministic SISO channel. So you remember from your previous course on communication, or if you take information theory, this is actually explained in details where this comes from, is that the maximum amount of information that you can transmit reliably is given by this channel capacity. So this channel expression that is log 2 1 plus SNR. Now this has many assumptions behind this. This assumes that you have really an AWGN channel. So you have something like in information theory is often written as X. You have a noise, and you have an output Y. And what you do is that you calculate the mutual information between Y and X, right, over a channel that actually is characterized by a noise here that is Gaussian distributed, that is AWGN. And you try to find the input distribution, so the distribution of X that maximize the mutual information between X and Y. And what you can show is that if you have a Gaussian noise here and you have an average power constraint for X, so expectation of X squared, let's assume X is real, for instance, or if it's complex like this, let's say is constrained. So the average, you have an average power constraint and you have a Gaussian noise. You can show that the distribution of X has to be Gaussian as well. And if you do that, you can show that the mutual information is actually equal to this relationship here. Right? So we'll not go into this. This is actually covered in the information theory course. If you take this, given by Chongling, this is very relevant, obviously. Right? You will understand where this expression comes from. But we'll not have time to go over this here. But just to give you an idea, is that you're really looking at the mutual information between those two. Then you're looking at what is the distribution of X that maximize this mutual information, and you're trying to find that. And if you find this, you show that actually X is Gaussian distributed, and this maximum mutual information is given by this relationship. And what it tells you is that essentially, if you transmit at a rate that is larger than this quantity, you're going to have errors, for sure. If you transmit at a rate that is smaller than C, then you can actually have reliable transmission, right? So C is the maximum amount of information that you could reliably transmit over this AWGN channels. It doesn't tell you how to do it, but it tells you there must be some ways to achieve this, but the maximum you could do it mathematically is given by this, right? So how would you do this in practice? Well, is using very, very strong codes. So for instance, turbo codes, LDPC codes, polar codes, and you would approach this capacity within a fraction of a dB, essentially. Right? And so the way it works is that if your SNR increase, you use constellations that actually increasing, the size increasing, and the coding rate also will change of those turbo codes, for instance. And by changing the modulation and the coding rate, you can adapt to the change in the SNR, and you can come very close to this capacity limit. So what happens if now you have a wireless channel? Well, if you have this system, this system model here, well, nothing's changed much. The only difference is that instead of having simply SNR, your SNR is written by rho h squared, right? So your rho is your long-term SNR, ES over sigma n squared that we have defined before, and rho is actually, and h squared is actually the strength of your channel, right? Because the channel is constant over time here, you have only one realization of channels for a very long period of time. You can simply look at what is the SNR that you have here, and then from there choose your right coding rate and modulation in order to come as close as possible to this capacity. That's what you would do in practice. For instance, you could use a QPSK in rate 1/2, or if you go to higher SNR, you would use, I don't know, 64 QAM, 256 QAM, and a rate, coding rate that actually will also increase in order to enable you a higher effective rate at the end and come very close to capacity. Right, so we'll not go into those code design. I will explain a little bit some aspect of code design in the MIMO case. But if you're interested in understanding the code design, you can take the coding theory. So this is given by Wei Dai. And so you will see that all those modules are actually related to each other when ultimately you design a wireless system, because you have, let's say, all the the MIMO processing that have to be connected to the error correcting codes, and all those are designed in order to try to get the highest possible rate, which is essentially given by the information theoretic bounds. Right. So, so what is the behavior of this now as a function of the SNR, as a function of this quantity here? So this is a log 1 plus x, right? So if your x is small, so at low SNR, so my x here is rho h squared, right? So if this x is small, you can approximate this quantity simply as x multiplied by log 2e. And so why is this interesting? It just tells you something important, that in the low SNR regime, when x is small, so when the SNR is small, your rate will actually scale linearly with the SNR, right? So actually, that's what's going to happen. Your x is equal to this. So that means that if you increase your SNR a little bit, your actually rate or your capacity here will increase relatively quickly at low SNR, linearly, right? So if you double this quantity, your rate will double. Now, on the other hand, if you go to higher SNR, because your log is something that is concave, right? Something like this. So here you're going to have a linear behavior at low SNR, but at higher SNR, you have something that is really concave. And so in that case, the log 1 plus x is sufficiently large, just behave as log 2x. And so what that means is that your log 2 rho plus h squared can be written as a sum of two logs. And so if you increase maybe your long-term SNR by a factor of 2, you actually only here benefit from an increase in the capacity by 1 bits per second per hertz. So imagine that instead of having rho, you now go to 2 rho. So here you had log 2 rho, and now you end up with log 2 rho, which is log 2 of 2 plus log 2 of rho. So this is equal to 1. So if you increase by 3 dB your SNR, whether you increase rho by 2 or actually you increase the channel gain is being increased by a factor of 2, that doesn't matter. You actually gain 1 bit per second per hertz, right? So what you see here is that actually at high SNR, you need to spend a little bit more energy because your increase of the rate with respect to the SNR is logarithmic, while at the low SNR is actually linear, right? So in the high SNR region, you actually have to spend quite a bit of energy in order to gain something in terms of rates compared to the low SNR region. Right, so this is always something that is important to keep in mind in communication systems. Your return on investment essentially is higher in the low SNR regime than in the high SNR regime. That's what it means. Right, so what if you have now multiple antennas, the SIMO and the MISO case? Well, we'll not prove this, but you can show simply that if you have a SIMO case, so you have multiple receive antennas, so I have one transmit and you have multiple receive antennas, so you have a vector channel. You can, and you have, sorry, here is you have a vector, so it should be bold, and you have AWG and noise. You can actually maximize, you can simply do MRC combining, because MRC combining in this case will maximize the SNR, and this is actually sufficient to achieve the capacity here. So what the capacity will be is log 2 1 plus rho SNR, and this 1 plus rho the norm of H, and the norm of H can be viewed as coming from doing a MRC combiner essentially. And so effectively what you have here is this is a column vector, this will be a row vector, so this is actually effectively a SISO system. This you have here an effective SISO system, and here you have a single scalar. So effectively after MRC combining you have effectively a SISO channel, and if you use Gaussian inputs, you actually end up with an effective rate that is equal to this, and this is actually the capacity of these channels when you have SIMO multiple receive antennas. Right. Right. One more thing actually I forgot to mention here. So the assumption to reach this is indeed you have Gaussian signaling. The second assumption is that your encoding, actually you assume your encoding is done over extremely long block lengths. In the limit, actually those lengths, those block lengths actually infinite, right? In reality, is not the case. You can never have infinite block lengths. Your code block is finite. But in the limit, where you can really have infinite block lengths and you have Gaussian signaling, you end up with this. Right. So in practice, so infinite block length is not possible, but Gaussian signaling is not possible as well, right? So to achieve this, in other words, your C here has to be Gaussian distributed. In reality, you use actually constellations, right? So you will not have exactly a Gaussian signaling, but by designing your constellation suitably, and you can actually achieve something that it comes close to this Gaussian signaling. That's what essentially it means. Right. So if you have a MISO channel, same thing. What you can do is actually you can do a maximum ratio transmission, and so you're going to end up with an effective SISO channels that has an instantaneous SNR given by this again, and your capacity of that deterministic channels for a given channel H, assuming you can really encode over a very long block codes, and your channels actually is really constant over that infinite infinite duration, you end up with actually a capacity that is given by this, right? So in this case, keep in mind you need to know the channels of the transmitter in order to do this beamforming. Okay. So we'll come back to this later on when we look at the MIMO case. Right, so this is a deterministic channel. So actually, my HK here, in other words, is actually equal to H, right? I could have dropped the K there because my channel is constant for a very long period of time, right? So here, HK becomes simply H is constant. Right, so second issue is what if now your channel is actually not constant, right? So you have, and this is what you have more in reality, your channel is never a constant over an infinite period of time. And it's not constant simply because you have always some form of mobility. Something moves, either you move or something around you moves, and so your channels will change. Right. Now, so here, what's happening is because of this change of the channel, the way we characterize the capacity is slightly different, and is through a single quantity that is called the ergodic capacity. So let me explain you qualitatively what this is. So let's imagine that I have now my channel is changing over time, and I have these channels like this, right, that I had before. Right, this is, let's say, the magnitude, for instance. And so that means actually at a given time instance k here, right, assuming this time instance or these channels is actually assuming I have a certain time instant k, I have a certain channel hk here. The rate over which at which the information could flow over this channel realization actually is equal to this, right? There are lots of assumptions behind this. I just want to give you here some qualitative interpretation here. So you can imagine that if you have a channel that change over time, your actually rate of information that will be flowing over each of those channel realization will actually also change over time. If you have a good channels, the amount of information you could transmit over the channels could actually be larger. In other words, the channels could support a higher rate. No. So that means actually, if I look at my average rate, so where I average using kind of sample mean here, I have T realization of my channel HK. So I go from, let's say, from 1 to T here. My average rate, so the average rate of information flow over those K realization of the channels will be given by simply a sample mean of this quantity. And so in the limit where T grows large, you can view h of k as simply a random variable, and you obtain an expectation of this quantity. Right? So this quantity is called the ergodic capacity of a fast fading channel. And the way you actually achieve that ergodic capacity actually depends on what you know about the channels, whether you know it at the transmitter or you don't know it. So let me explain this a little bit. So let's imagine that I have this here. And let's imagine first that I know HK at the transmitter, right? If I know HK at the transmitter, that means that I could use a modulation encoding rate in order to adapt my rate of transmission as a function of this channel HK. So I could choose my modulation encoding rate in order to come as close as possible to this, right? So what that means is that this block length here has to be still sufficiently long in order for me to actually encode, over this channel. But I could, because I know H of the transmitter, I could adjust the rate of the transmission. Right? And so what it means is actually you use a variable rate code. So variable rate is simply means that actually every time your channel changes, you use a different code and a different modulation. You use, for instance, QPSK rate 1/2, and if your channel becomes better, you use a 16 QAM and rate 7/8, for instance. Right. So you adapt your rate of the transmission, the code and the modulation to the channel states. And so on average, what is the average rate you will get will actually be given by this. Right. Now your code here, what is important is that your code words here will only span one realization of the channel here. Right. So your code word, you could say they do not need to be that long, in other words, because you don't need, strictly speaking, to actually encode over many realization of the channels. You know your channels, and so you can adapt to that realization. So you could simply have a code word that is not that long, but the code words its effect will be to average out the noise. Right. So the use of the error correcting codes here will be really to get rid of the effect of the noise. Right. All what I'm saying here is a little bit qualitative, because strictly speaking, to achieve this rate here, to achieve that, you will need to have infinite block lengths. Right. So, but which is never practical. But what it says is because you know H of the transmitter, you don't need to really encode over many realizations of the channels. You could just encode over each realization of the channel, right? And hopefully this will give you some code words actually are smaller, right? Now you only average out the effect of the noise. On the other hand, if you don't know the channels of the transmitter, then you cannot change your modulation encoding rate as a function of HK, right? But if your channel is changing and you have the ability to encode over many realizations of the channel, then what you can show is that you can still achieve the same capacity here, the same rate, the ergodic capacity, when you actually transmit at a fixed rate given by this rate here. So you choose a modulation encoding rate according to the ergodic capacity, not according to the instantaneous one, because you don't know H at the transmitter, but according to the ergodic capacity, and you transmit with that fixed coding scheme, but that scheme has to be long enough in order to span many realizations of the channel, right? So that's what it says. So those are actually two different strategies to achieve this ergodic capacity. The first case that you know the channel, so you can adapt, and you use a variable coding scheme, so you can adapt to the channel realization. The second one, and you average out only the effect of the noise. The second one here is that you transmit at a single rate, a single fixed rate that is given by the ergodic capacity. And what this will do is that it will average out the effect of the noise, but it will also average out the effect of the channel fluctuation. right? Because you span, the code work will span many realization of the channel. Okay, so to understand this in more detail, we have to go into the information theory. Even I think Chong does not cover this, right? This notion of ergodic capacity. But this is essentially what the information theory tells us in terms of designing wireless systems. Right, so same as what we did before, you can then look at low SNR, high SNR by taking the expectation here. At low SNR, what you can show is that we had this quantity here. Right, if I take an expectation of this, I'm going to have expectation of that. Expectation of the channel gain here is equal to 1. So I'm going to have simply rho multiplied by log 2e. Right, so that's what happens. Same interpretation. If you increase the SNR here, your ergodic capacity will increase linearly with this SNR. Right. And what you see here is that your ergodic capacity here at low SNR is actually the same as an AWGN channels. This is the same as if your channel here was your channel gain here was simply equal to 1. Right, so you didn't have wireless channel, your channel gain is equal to 1. So your obviously expect, if it's constant, the expectation of this is equal to 1, obviously. But this is always something we have if the channel is fading or if it's not fading. But what it says is that actually at low SNR, your ergodic capacity, if you have a fading channel, your ergodic capacity will actually be the same as if you have an AWGN channels where actually your channel is constant, equal to 1. Right. Now, the high SNR, things are a bit different. At high SNR, you're going to have the log that we had before, so the log 2 rho a square. You can break this into 2. Then you can take the expectation of this. This is at high SNR, so actually the 1 plus I discard. And now I take the expectation of this term. Now, this is here a random variable. Right, circularly symmetric complex Gaussian inputs, right, for h. So the magnitude is Rayleigh, the magnitude square is exponential, and so you can compute this expectation, and you can find actually this is minus 8.83 bits per second per hertz. Right. So what that means here is that because your channel is actually fluctuating, your ergodic capacity will be decreased by 0.83 bits per second per hertz, compared to the case where you had a constant channel equal to 1, right? AWGN channels. So your ergodic capacity is actually decreased compared to the AWGN capacity, right? AWGN capacity again at high SNR is simply equal to this. Right? So what in other words, it means actually you're having fading here, fluctuation of the channels will actually decrease. Will lead to a loss in terms of rate compared to the case where you have the channels that is completely flat, completely constant. Right. That's what it says. Good. So this is fast fading channels. Now you can have the opposite problem, which is that you're not in any of those two scenarios here, right? So either you don't know the channels at the transmitter and you cannot adapt to those channel conditions and change your coding rate according to that, or you don't know the channels at the transmitter like here, but you don't have the ability to transmit over many realization of the channels because simply the channel is changing too slowly, right? So in that case, you end up with this kind of slow fading channels, which I can write is like this. So I have again those realization here of my channel. But now my channel here, this length here, is actually quite long compared to my encoding block, right? So in that case, I'm in another scenario because if I don't know the channels at the transmitter, I cannot adapt my rate according to the channels, and at the same time, I cannot encode over many realization of the channels, so I cannot achieve this ergodic capacity, right? And so the problem here is that you end up with the notion of outages. So let's imagine the following. I don't know my channels at the transmitter. So let's imagine I transmit here at a certain rate, right? If I transmit at a certain rate and my channel is not good enough, then I will have errors at the receiver, right? If the channel happens to be good, then it's okay. But there is a likelihood that because I don't know the channels of the transmitter, there is a likelihood that actually I will not be able, the channels will not be able to support the rate at which I transmit. And so this is a problem. So if you have H1 here, H2 there, and so on, the maximum rate that this kind of channel realization can support will be again log2 1 plus rho H1 squared, right? But if I transmit at the rate here, R, that is higher than that, right? For sure, during that time here, I will have errors, right? So this is where the notion of outage comes in. Outage is really when you transmit at a certain rate over fading, over channel that actually is slowly fading, and you only have the ability to encode over one realization of the channels, not over many of them, then what can happen is that your rate may not be supported by the wireless channels. And so the reliable transmission will only occur if your channels is better, if your channels can support the rate at which you transmit. So for instance, here, those channel conditions, the rate that the channels can support is higher than the rate at which I transmit. And so here I'm going to have reliable transmission over those channel states. But in those ones here and there, the rate at which I can transmit R here will be higher than the rate that the channels can support. I'm going to have outage. Okay, so this is what it means here. You're going to have reliable transmission, no, if your rate at which you transmit is actually smaller than the rate that the channels can support for a given realization of H. Right? And you're going to have outage whenever the rate at which you transmit is larger or higher than the rate that the channels can support. Right? Now, because H is a random variable, you don't know it at the transmitter, what you're looking at is what is the probability that the rate is higher than that. That will give you the outage probability. That will give you the percentage of time, if you like, or the percentage of channel realization for which you will not be able to transmit at a rate R. Right? That's your outage probability. Is the probability that your channels will not support your transmission at your target rate R. Okay? So if you compare this with what we had before we had with the ergodic capacity, we had this, right? So you can view this kind of random variable, and you take the expectation of that random variable. Here, you view this as a random variable, and what you're looking at is actually the kind of CDF of that random variable. Right? You're looking at the tail of that distribution. So you look at a different characteristic of that random variable, if I can qualitatively explain it this way. Right? So in other words, because you don't know H at the transmitter, you cannot adapt instantaneously to this channel. So what you hope is actually the channels will be good enough, right? And unfortunately, the channel is not good enough. Well, you will use your packets. Okay. You don't know the channels of the transmitter. If you have a slow fading channel, the channel changes very slowly, but you know the channels of the transmitter, not an issue, right? Not an issue at all. You can always do what we did before. You can always adapt your rate according to your channels, right? So if you know H the transmitter, I can always adapt my rate according to that. If you have slow fading channels that you don't know H the transmitter, you're not able to adapt your rate in any ways. So you just hope that actually the channels can. Okay. So the way this is analyzed is through this notion of diversity multiplexing tradeoff. that essentially tells you if I transmit at a certain rate R, how does my outage probability, and typically at high SNR, right? So if I transmit at a certain rate R, how does this expression behave? And we're going to look at this in the limit when we have a large SNR regime, right? So let me write R as the following. In the high SNR regime, I will write R simply as GS, which I call multiplexing gain, multiplied by log 2 rho. So GS is the pre-log factor of the SNR in dB. And what it says is that if I increase GS, it means that actually my rate at which I want to transmit will increase faster with my long-term SNR, right? So I have a long-term SNR, for instance, 10 dB. I have a channel realization H, which I don't know. But what I would like to do is, because I have higher SNR, let's say 10 dB, or I move to 20 dB, I want to actually increase the rate of transmission. And so GS will tell you how quickly you want to increase your rate with the SNR, essentially. Your long-term SNR, right? Now, GD here will be actually the slope of your outage probability. So you can view this, your long-term SNR, outage probability, and the slope here at high SNR will tell you this, this diversity gain. So you can view the outage probability as something like rho minus GD. Okay, this is very reminiscent to what we have done before with the error probability, right? But instead of having error probability here with a specific constellation, modulation, and so on, here I'm having an outage probability. So my outage probability is given by this, right? And what I'm looking at is how quickly can I increase the rate here? So how quickly can I increase GS? And if I increase GS, what is the impact of the slope of this outage probability? And so there you have a relationship between, when you have slow fading channels, between, if you like, reliability and transmissions rate. So if you increase GS, you want to transmit at a higher rate. But this will actually lead to actually an impact in terms of reliability that will be measured in terms of outage probability, right? If you have a higher outage probability, that means that your transmission is less reliable in a way, because you're going to have more channel realization for which you cannot support that rate R. Right? So this multiplexing gain tells you how fast the transmission rate increases with the SNR. The diversity gain tells you how fast the outage probability will decay with the SNR. And there is a trade-off between the two. You cannot increase your transmission rate as you like without having a loss or actually a hit in terms of outage probability. Okay, that's what it says. So the way you can look at this is the following. If I'm looking at my outage probability, I have this, and I'm writing here my rate. This is R, just wrote before, right? Let's imagine that now I remove the log, right? I have log here, log there, so I can simply write this, right? My event is the same, right? Now, if I have high SNR, the 1 plus can be removed. And so I'm going to have an outage essentially when my channel realization is smaller than this quantity. So if your rho is your long-term SNR, what you see here, you're going to have an outage whenever your channel realization, the channel strength, is smaller than this quantity, right? So this is 1 over rho 1 minus GS, right? So let's imagine you fix GS to a constant. So if your channel realization is smaller than this, right, you're likely to have an outage. That's what it says. Like, how often are you going to have an outage? Well, this is exponentially distributed. So the probability that having an exponentially random variable being smaller than a certain quantity is equal to that quantity. This is a property of exponential random variable. So what that means is the following. That probability will be equal to that. That probability, that outage probability will be equal to that. So in other words, you have an outage whenever this occurs. Whenever this occurs, you're going to have an outage. That means actually you will not be able to recover the transmitted packet. And that outage will occur with a probability given by that. So you're going to have an outage whenever your channel is smaller than that. And this will occur with a probability given by that. So what that means is that as you increase rho, your outage probability will decrease, right? That makes sense. But as you increase GS, your outage probability will actually increase, right? If you have this is the same as this, right? So if you have GS equal to 0, if GS equal to 0, you're going to have 1 over rho. If GS is equal to 1, you're going to have here rho to the power 0. So in other words, you're going to have something that is constant. So if GS is equal to 0, if you have rho, if GS is equal to 0, you're going to have an outage probability that will decrease as 1 over rho. If GS is equal to 1, you're going to have an outage probability that will be a constant, right? So this is what it means. GS tells you how fast you want to increase the rate with the long-term SNR. And what you see is that if you want to increase the rate very fast, GS is equal to 1. So I want to increase the rate as GS log 2 rho. So if GS, my multiplexing gain will be between 0 and 1. At most, I can increase as log 2 rho, because that's the maximum rate at which I could transmit according to Shannon expression. Then, if I do that, I will have an outage probability that will be constant. That means actually, whatever my long-term SNR, I will have, actually in the high SNR regime, I will have always an outage probability that will be constant. In other words, if you transmit at GS that is equal to 0, so in other words, GS equal to 0 does not mean you transmit as a 0 rate. It just transmits at a rate that is constant, right? Because it's in the high SNR regime, it's according to this. So strictly speaking, if I write, it's always plus a constant, right? But in the high SNR regime, if I take the limit of GS log 2 rho plus C divided by rho, log 2 rho, and rho goes to infinity, right? The C is a constant divided by log 2 rho will be equal to 0, so this will be equal to GS, right? So when I'm writing this, it means that you can always have a constant rate additionally, right? But GS equal to rho, to 0 would simply mean that your rate does not scale with the SNR. Your rate is actually constant, right? If GS is strictly larger than 0, it means that your rate will increase slightly with the SNR, logarithmically. If GS is equal to 1, your rate is really logarithmically increasing with the SNR, right? So if GS is equal to 0, now I have a constant rate. So I transmit at a constant rate, but I have an outage probability that decreases 1 over rho, right? So I'm going to have a more reliable transmission because I have my outage will decrease as my long-term SNI increases. Okay, so this is the trade-off between multiplexing gain and diversity. Multiplexing tells you how fast you want to increase your rate with the SNR. The diversity tells you how quickly here your outage will decrease with your SNR, and you cannot do both. If you want to have, if you want to increase your rate with the long-term SNR, you will have a hit in terms of outage probability, in terms of reliability. Now, what we had here, right? I was saying GS equal to 0, I transmit with a constant rate, and I have then an outage probability that scales as 1 over rho. This is actually reminiscent to what we have done before. You remember when we did the error probability calculation of, let's say, a QPSK or or MPSK or MQAM or even BPSK, and we had just a SISO case. We were saying that the the error probability was scaling as 1 over rho, right? This is what we had here. Let me take this again, that you see what I'm talking about. Right, you remember this when we're looking at the impacts, we had a SISO case and we had 1 over rho here, right? You remember what we were saying here is that if rho increases, I have essentially a decay of the error probability as 1 over rho. But the assumption here is that I was always using a BPSK, right? I was always using a BPSK. So even if my long-term SNI increases, I always transmit with BPSK. My rate is always constant, right? So this scenario corresponds a little bit to saying my GS is equal to 0. I transmit at a constant rate, and this is why my error probability was decaying as 1 over rho. And this is what the outage probability tells us as well. If you transmit at a constant rate, then indeed, in terms of reliability, the outage probability will be as 1 over rho, right? But if we had here transmitted with higher constellation as rho increasing, then we would have a different behavior. If I increase my rate proportionally to the rate, in the limit of high SNR, I will not have simply a 1 over rho there, right? That's what it says, right? So those two, the outage probability and the error probability analysis here actually in line with each other, in the sense that when I transmit with a constant rate, indeed, I have an outage probability and an error probability that will scale as 1 over rho, right? Good. So, so all what I was saying is actually summarized here. Right. So that's the important thing. When you have slow fading channels, you don't know the channels of the transmitter. Essentially, you cannot avoid having some deep fade. You will always have some channel realization over which you you cannot have reliable transmission, and you're going to have an outage, right? And how often you're going to get this outage depends on how you fix your rate of transmission. If you increase your rate of transmission with the SNR, you're going to have more drop. If you have a fixed rate, whatever the SNR, your drop will be decreased essentially. The likelihood that you're going to have an outage will be decreased. Right. Any questions? Yeah. Again, feel free to interrupt me. Right. Right. So you can do this for MISO, SIMO. The idea is the same, so we'll not go into those details. But the idea is the following. So now your rate in the SIMO case, instead of having log to 1 plus rho multiplied by the absolute value of h, now the absolute value of h is now replaced by the norm of h in the SIMO case. And the idea of the outage probability here in the SIMO case is the same as what we had in the SISO. This is the rate, right, that the channels can support, the channel h can support, and this is the rate at which you transmit. If your rate is higher than that, you're going to have an outage, right? Now you can analyze this. This is again is done in the MIMO book. You can analyze this, and you can show that actually this outage probability will behave as 1 over rho to the power nr, and the power nr comes from the fact that you have nr receive antennas. So h here is actually an r dimensional vector, right? You have h is h1 all the way to hnr because you have nr receive antennas. So nr independent random realization, random variables. So this is assuming always you have relay fading. So in this case here you have relay fading for each of them. They're independent from each other. So you have circularly symmetric complex Gaussian random variable. They're all independent from each other. Right? Again, so your outage probability here will decrease faster if you increase nr, right? So this is again if you have a constant rate, if you have GS equal to 0, and this is reminiscent to what we have seen with the error probability. With the error probability, we saw that if you do maximum ratio combining, your error probability with a fixed rate, with let's say QPSK transmission, will actually decrease as 1 over rho to the power nr. Here, what it says is that even more from an information theoretic perspective, if you like, indeed, your outage probability will decrease like this. And now you can do the same at the MISO case. It's slightly different in the MISO case. It's given by this. So recall that you have no knowledge of the channel of the transmitter, right? So if you have no knowledge of the channel of the transmitter, you cannot do maximum ratio transmission. And what you can show is that it's a bit more complicated. You can look at, strictly speaking, you can look at what is the strategy that maximize or minimize the outage probability. And you can show that this strategy is such that actually the rate is equal to that. So I will not go into those details, but the main message I want to deliver here is that your outage probability, if you have a constant rate, will decay as rho to the power nt. So if you increase the number of transmit antennas, you're actually going to have a decay of the outage probability that is proportionate to the number of transmit antennas, right? And this is a bit reminiscent to what we had with Alamouti, for instance. Alamouti, you don't know the channel of the transmitter, right? But we saw that the error probability is 1 over rho square. So the outage probability will be also 1 over rho square. Okay. Good. So this is really some crash course on some of the basics of wireless for you to understand this notion of really slow fading, fast fading, and what is the implication of actually the scheme that you can use behind this. Really, the difference is the slow fading. When you don't know the channel of the transmitter, you have this issue of actually the channels may not be able to support your rate. While the fast fading, even if you don't know the channel of the transmitter, you're able to actually encode over many realization of the channels. And so the outage will never occur as long as you can encode over many realization of them, and then you can achieve the ergodic capacity. So those are two different notions that occurs when you play with fading channels. Right. Okay. So with this, finishing the first part of this module. So you'll see coursework 1 actually deals with this first part. You're going to have to simulate some of those basic schemes, SISO fading and MISO and SIMO over fading channels, and see the performance that you get in terms of error probability and measure the diversity gain that you obtain and the array gain and these kind of things. Right. So now what we're going to do is start looking at MIMO. So instead of having single antennas at either the receiver or the transmitter, like we have in SIMO or MISO, where we had this, right? This is my MISO, this is my transmitter, this is the receiver, and I had SIMO. I have this again, transmitter and receiver. Now I'm going to look at a more general case, and we'll see this more general case essentially is I can have multiple transmit antenna, multiple receive antenna. And so MISO, SIMO, SISO are all particular instances of a MIMO framework, if you like, because in the MIMO framework, you can always put some of those antennas at the transmitter, the receiver equal to 1, and then it boils down to the SIMO, MISO, or the SISO case, right? But the MIMO gives you additional benefits. And now instead of playing with vectors or scalars, we're going to start playing with matrices, because we'll see the channel matrix now will be the channel will be actually a matrix. Will be a matrix that will link all those transmit and receive antennas together, right? And the fact that we play with matrices, we're going to have some additional benefit in terms of typically in terms of rates. Good. So we look at basics of MIMO here. Then we look at the MIMO channels. This will cover a few lectures, right? All those subsections here. What is the MIMO channels? What happens in the MIMO channels? Then we're going to look at the capacity of the MIMO channels and how we can achieve that capacity. And we're going to look at some processing we do with the transmitter and the receiver. Then we look at some more details onto transmitter and receiver strategies. And we will come back to the Alamouti schemes, for instance, but in a more general framework that is called space-time coding and processing. And then I will go over quantized precoding as well. And we'll see what happens when you may know the channels, but not perfectly the transmitter. You know it only in a quantized version of it. And this is will be also all very helpful when you look at coursework 3. So you will see what we do here. All those stuff will play a big role when in coursework 2, but also a lot in coursework 3. Right, reference book. lots of those stuff comes from the MIMO book, those different sections here. Some aspect I cover in David Say's book as well, but maybe not in the same details as here. Right, so let's look at basic of MIMO. And so let me remind a little bit what we have done so far so that you understand the flow of ideas here. Right, so the system model we had is the following. We had the SISO, SIMO, MISO. And so in the SISO, we had just scalar here and scalar there, right, and scalar for the nodes. In the SIMO, we had a vector here, a vector there, and we had a vector channels there. Right? And in the MISO, in the case where we had perfect CSIT, we had a scalar the receiver, scalar for the noise, and we had here actually a vector at the transmitter site, right? Because we have multiple receive antennas, and so we have a vector channels H as well. Right? Those elements of H, right? They are fading coefficients in general, right? We assume that actually a circularly symmetric complex Gaussian random variable, so the amplitude is Rayleigh, the phase is uniformly distributed. We looked at the notion of diversity gain and array gain, right? The diversity gain is the slope of the error probability, or you can view this also in terms of outage probability, depending on whether you're looking at the practical scheme using a specific, constellations, or you're looking at a more, I would say, a more information theoretic metrics like the outage probability is always the slope of that probability with the SNR. And the array gain is how much your average output SNR increase compared to a single branch SNR. So it's a gain in terms of shifting. This is your array gain, so it's a shift along the SNR, and the diversity gain is actually a change of the slope versus the SNR. So SIMO, MISO, selection combining, gate combining. MISO case, we had the match beam forming and we had the Alamouti schemes, right? So those are the main schemes that we looked at. Now, in the MIMO case, we will come back to all those notions and see what happens now when we have multiple receive antennas. Right? So the first thing to do is to try to take this and generalize this to the case now we have multiple antennas, a transmitter and the receiver. So the first thing is about the fading coefficient. So now we have, let's say in the example we have here, right? If I have two transmit antennas and two receive antennas, I'm going to have now 4 fading coefficients. You can view this as you have essentially kind of 4 SISO links. You have a SISO link between antenna 1, receive antenna 1, transmit antenna 1, receive antenna 2, transmit antenna 2, receive antenna 1, and so on. So you have 4 SISO links. So you need to model those 4 of them. Right? So if you have NT and R antennas, so NT transmit antennas and R receive antennas, you're going to have NT by NR channel coefficients in a way. Right. Now, the path loss, if you have a spacing, if you take this, if you have the spacing between the antennas here is relatively small, the spacing here is relatively small, and the distance here is relatively long, what's happening is that actually the path loss and the shadowing for all those 4 links will actually be the same, right? Because the path loss and the shadowing will not change, if you change over this dimension of the array. If you just move by half a wavelength, by let's say at 7 or 8 centimeters at 2 gigahertz, the path loss and shadowing will not change. But what will change is the small scale fading, right? So your path loss, your shadowing will remain the same for all those 4 elements, as long as you have the spacing is not too large among those antennas. But what will change is those coefficient H, the small scale fading, and you're going to have all those 4 coefficients will be different from each other, right? Now, this holds when you have small antenna regime. If you have very large antenna regime, you have like massive MIMO, where your antennas are spread over a very large surface, then this assumption may not hold anymore because the distance between the antenna may not be negligible anymore. And so some of those things may change a little bit. But as long as this distance, the array size is actually small compared to the distance here, you can reasonably approach this by saying your shadowing and your fading is actually the same. We're going to assume this in the coursework as well. Good. So let's imagine now I'm going to have multiple inputs I will transmit, right? I'm going to have a vector here at a certain time instant k that will span nt dimension here, right? Because I have nt antennas. And at the receiver, I'm going to have a vector also that have nr dimension because I have nr receive antennas. And so now I'm going to have a system model at a certain time k that will be equal to this. I have my received observation vector, nr dimension. I have my transmit signal vector that will be dimension nt, and I have a prime here because this quantity will be related to ck. It depends on what kind of processing we do, right? And I have a vector here that is dimension nr, which is our AWGN noise. I assume again is a wide noise, time and space. And now I have a hk here that is not a vector anymore. It's a matrix. It's a matrix. It's a nr by nt matrix. Right, because I have NT transmit antennas and NR receive antennas. We're gonna assume again that those coefficients I had before. So let me write an example of this here that you understand. Let me write this here. So let's imagine I have. Let me write it slightly. I put the transmitter here and the receiver there. Right. Sometimes I change this, but you see why I do this. Sometimes it's actually easier to do that. So let's imagine I have this H11. So in my channel matrix H, I will have, that's the channel gain between transmit antenna 1 and receive antenna 1. I have here what I'm going to have from transmit antenna 1 to receive antenna 2. This is what will be H21. H21. So this is the channel that goes from the transmit antenna 1 to the receive antenna 2. H12, H22. So this is from transmit antenna 2 to receive antenna 1, H22 from those two. So this is H22, H12, H21, and H11. Okay? So I'm going to assume that expectation of Ij, same as what we did before, is equal to 1. So the fading on average does not increase the SNR, the received power. And so if I take a sum of this, expectation of H11 square plus H12 square plus H21 square plus H22 square, this will be equal to 4, right? This sum here, you can write this more easily by the following. This will be the square of the Frobenius norm of H. What is the Frobenius norm? Is essentially the equivalent of what we had with a vector. We had this, where you take this is the square root of the sum of Hi square, right? Here, so if you take the square of this, you remove the square root. Here is actually will be the sum of the square of all those coefficients in that matrix, right? And so we'll use this quite a bit. It tells you essentially what's the energy of that channel, right? It's the sum of the energy of each of those coefficients. So the sum of the channel gain of the strength of each of those 4 channels. So you can view this as if you have a higher Frobenius norm, you have a higher energy in your channel. Right, so expectation of this is equal to 4 in the example I gave you. In general, it will be equal to NT and R, right? Because you have NT and NR, NT multiplied by NR channel coefficients. Right, we look at 2 different schemes. The first one when you have channel knowledge of the transmitter, the second one when we don't have channel knowledge of the transmitter, right? Again, this is used heavily in practice, depending on the mobility you have or what type of channels you're looking at, whether you're actually looking at transmitting data information, your YouTube video, or you're looking at control information, then you're going to have different assumptions there. Right. I have a reminder here, basic of linear algebra. I will not go over this, but I may come back once in a while, right, just to make sure that you're familiar with this. Just to highlight a few things. So the Frobenius norm is here. We just mentioned that. The Hermitian matrix, right? The Hermitian operator is the conjugate transpose. We're going to play a Hermitian matrix is when a matrix is equal to this Hermitian, so it's equal to this transpose conjugate. Unitary matrix is when you take a matrix, you take its Hermitian, you multiply by itself, and it's an identity matrix. Vector orthogonality, you all know that, right? The inner product of two vectors is equal to 0. And then we're going to play with a singular value decomposition where you have a matrix H, a certain dimension, and you break this into the left singular vector, here, the right singular vector, and then a matrix of singular values, right? And we're going to play with eigenvalues decomposition as well, which is for the case where you have a Hermitian matrix, and you will see in the MIMO context, we're going to play a lot with this kind of matrix, H Hermitian H. So this is actually a Hermitian matrix, because if you take the Hermitian of this, it's still the same matrix. In that case, you have actually an eigenvalue decomposition, because the left and right angle vectors here actually the same in that case. And so you can relate this to what we have here. If you have A is H Hermitian H, essentially what you're going to have is H Hermitian will be equal to V, this U, and in general, let me write this, and H Hermitian H gonna be V, this, multiplied by this, multiplied by that, right? And so here, you know, the left singular vector are actually unitary matrices, so this will be equal to identity matrix. And then you're gonna have this multiplied by this, right? They are actually real there, so actually it doesn't matter if you have H there, right? You're going to have real coefficient, so that's why you can have simply a square, and this is called eigenvalues. So the eigenvalues will be the square of the singular values, right? I guess you have all done this in your linear algebra modules in undergraduates. All right, so we're going to play with this. And you see the SVD or EVD will actually have a key role in MIMO, because we're going to decompose this into those left and right singular vector, and the processing will be based on that. All right, so those are the main things we're going to play with, and I will come back to some of those later on, some operation, but this is not so important at this stage. Right. Okay, so first thing we're going to do, let's try to understand how we can use the Alamouti scheme. We all know Alamouti now. How can I use Alamouti when I have two receive antennas? So what we did is one receive antenna, right? Two transmit, one receive antenna. How can I do the same when I have two receive antennas, right? You can apply exactly the way we did with the MISO case. So let's imagine I have a 2x2 channel. So now I have 4 coefficients. When I do what we had before, let me write this. I have transmitter, receiver. And so remember what we did with Alamouti. We transmit C1, C2. It will be divided by square root of 2. I omit here for simplicity, but it will be in the equation. And then we were doing minus C2 conjugate and C1 conjugate, right? So now we can do that, right? But the difference with what we had before is that instead of having only one receive antenna, we're going to have 2 of them, right? So when I look at the first time instant here, so this is T1, and then you have T2. The first symbol period, I'm going to transmit C1 and C2 across this channel matrix H, and I receive an observation Y1 at time 1, right? Now, before we had a scalar there. Now we have here, we have a vector, right? We have a vector, we have NR receive antenna, so we have NR dimensional vector. So in this case, you have a 2-dimensional vector if you have 2 receive antenna. Same for the second time instance. Here you have second time instance. So I transmit now minus C2 conjugate, C1 conjugate, travels across my MIMO matrix. And I have again another observation, 2-dimension with these 2 receive antennas. So you remember what we did before? We were taking the conjugate of Y2, right? Let me take this again so that you follow. So we were taking the conjugate of Y2, blah, 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 right here. Right, we were taking the conjugate of Y2, and then we were stacking up those observations here, right? Here. right? So let's do the same thing, but instead of having scalar here and there, I'm now going to have vectors because I have multiple receive antennas, right? So let's do that. Let's conjugate first, and then let's stack up all those observations. Oops, here. So I conjugate here, and I stack them up, right? So I have now, what is the dimension of this? It would be 4 by 1. I have 2 observations, and each observation is a vector of 2 dimensions. Right? Now, because I have taken the conjugate, what's going to happen is that I'm going to take the conjugate of that matrix here. So what's going to happen is that you are going to end up with a matrix here similar to what we had before. What we had before was actually this line. If you had only one receive antenna, you have this and this, right? The channels related to the first receive antennas, actually those two, right? And so this is what we had earlier on in when we had the MISO case, and we were simply calling H1 and H2, right? Because I had a single receive antenna. So the first index here is for receive antenna 1. Now, additionally, now because I have multiple receive antenna, you see I have now the observation or the channel gain corresponding to the second receive antennas, right? So I encourage you to write this at home. You can do that. You take the complex conjugate of Y2. So you're going to have some complex conjugate here. You can reshuffle the terms, and you can write this into this matrix form. Right? Now, what is the magic here again is the fact that, similar to what we had before, if you take this effective channel matrix and you multiply it by its Hermitian, what you're going to end up with is a scaled identity matrix. It's an identity matrix that is being multiplied now by the Frobenius norm of H. Before, for the SISO case, we had this. Not the SISO, the MISO case with Alamouti with single receive antenna, we had this, right? We did that. Now we're going to have actually not H, but we're going to have the matrix H. So instead of having 2 coefficients here, now we have 4 coefficients there. Okay, but this is very nice because again, as the output after doing that, my observation Z after doing this linear processing, I'm going to have here my C1 and C2. They will not see any interference with each other. So I can take the first observation here and perform a SISO maximum likelihood detection to obtain C1. I can take the second observation and obtain a maximum likelihood detection of C2, right? Importantly, this channel matrix here again has to be constant between the time 1 and time 2, in the same way as what we did with the original Alamouti scheme. Right, so what will be the diversity gain of these schemes? Well, you can imagine already, if you have this effective SNR is proportional to this, right? You have 4 coefficients there, right? If you have 4 coefficients, you have H11 square plus H12 square plus H21 square plus H22 square, right? This is chi-square distributed, right? Because you have 8 degrees of freedom in there, right? Because each real part and imaginary part is complex Gaussian random variable. So essentially, because of this, you're going to have a diversity gain of 4, right? Remember, this is a bit the same. This will give you the same diversity gain as if you have a SIMO system. If you have a SIMO system, if I have a SIMO system where I have a transmitter and I have 4 receive antennas, and I have H1, H2, H3, and H4. And I'm going to have, if I do MRC, I'm going to have a channel gain or SNR that is scales with this, where H is H1, H2, H3, and H4, right? Diversity gain here, I have NR equal to 4, so I have a diversity gain of 4 here, right? Now you should be familiar with this. Well, here, I have the same. I will have also a diversity gain of 4 because effectively I have 4 independent Shirley coefficients that are all circularly symmetric complex Gaussian random variables. So I'm going to have diversity gain of 4. But instead of having 1 transmit antenna and 4 receive antenna, now I have 2 transmit antennas and 2 receive antennas. So I have added 1 here, but I have removed So I have added one here, but I have removed two at the receiver, right? But the processing is not simply MRC, it's based on this Alamouti encoding here, okay? So that tells you that you can have different antenna configuration that will give you the same diversity gain. You could have two transmit, two receive will give you a diversity gain of 4, or you could have 1 transmit and 4 receive will give you a diversity gain of 4, or you could even have 4 transmit and 1 receive. You could also have a diversity gain of 4, right? If you do maximum ratio transmission, you can have a diversity gain of 4 if you have 4 transmit antennas and 1 single receive antennas, right? So different antenna configuration can give you the same diversity gain. Now this is useful because imagine imagine you have a transmitter with single transmit antennas, but then you need to actually have 4 receive antennas at the receiver, and you also have a diversity gain of 4. Maybe in some system it might be complicated to do that. So what you may want to do is to balance, the number of receive antennas, the number of transmit antennas, right? Now this is done for a 2x2 case, and so you get a diversity gain of 4, so you get essentially here the error probability will scale as a factor of 4. Right? You still have a factor of 2 here in your output, average output SNR, again because you have the factor of 2 here, right? So nothing has changed there. The same is there. Right. Now, what if you have 2 transmit antennas? So I have 2 transmit antennas. NT equal to 2, but I have NR receive antennas more than 2, right? So my channel matrix H is now NR by 2, right? I can still do the same thing. I can still do C1, C2 minus C2 conjugate, C1 conjugate. I can still apply Alamouti. If my channel is constant over those 2 time instants, I can do exactly the same thing as what we just did, right? But now I'm going to have NR receive antennas. So in the Y here, I'm going to have NR dimensional vector, NR dimensional vector. So I'm going to have here 2 NR dimensional vector, right? And so you're going to have a channel matrix H. You're going to have, again, effectively, a Frobenius norm of H here. But now you're going to have a sum here of how many coefficients I'm going to have in H. I'm going to have 2 multiplied by NR coefficients, right? So I'm going to have a diversity gain. My diversity gain now will be equal to 2 multiplied by NR. So I benefit from the NR receive antennas, but additionally, I benefit from the 2 transmit antennas. So I have a total diversity gain that is 2 times NR, right? So compared to the SIMO case, my diversity gain is now multiplied by 2. In the SIMO case, I get the NR diversity gain. Now in the MIMO case with 2 transmit antennas, I have the diversity gain is multiplied by 2. Okay? Right, so that means that your error probability or your outage probability, all those things will drop even faster. Instead of having something like this for SIMO, for instance, now going to have something that drops faster. Sorry, I don't know why. On the left side here always has trouble. This is SIMO, and this would be the MIMO with 2 transmit antennas, right? So you're going to have an increase in the slope. Oops, sorry, I'm going to have to stop here. I didn't realize we're already 11. Right, so thanks a lot. Feel free to send us questions if you have any. And don't forget you have the first class on Monday. Thank you. Bye-bye. Take care of yourself.